Welcome to the deep dive, where we grab a stack of research and pull out the really interesting stuff for you.
Yeah, it's a deep dive into some fascinating topics. You know, those rabbit holes you go down on Wikipedia late at night?
Oh, we do the digging for you and present those really cool
I
takeaways.
think you can just sit back and absorb it all.
Exactly. And today's dive is going to take us way out there.
Out there is, right? We're talking about the universe.
And like what it's made of and how that view has changed so much over time.
You know, we've got these sources and they're like mind-blowing.
Seriously mind-blowing. So how about we make that our mission for today?
Okay.
To understand how our picture of the universe has been like redrawn over time.
Like, what were those key moments, those big surprises?
And what are the big questions that we're still grappling with today?
Absolutely. The mysteries that are still out there.
The mysteries. Okay, so to kick things off, let's talk about noise.
Noise.
But not just any noise. Like, this is a particular kind of noise that really changed things.
Okay, I'm intrigued.
Yeah, so we've got to go back to Bell Labs and these two guys, Penzias and Wilson.
Ah, yes, Penzias and Wilson.
What were they up to?
So picture this, right? It's the 1960s, and they're working with this huge horn antenna.
Like massive, right?
Yeah, massive. It was originally built for satellite communication, like Project Echo and Telstar.
Oh, wow. So like the early days of space exploration?
Exactly. But once those projects were done, Penzias and Wilson thought, hey, let's use this antenna for something else.
Repurpose it.
Repurpose it. Yeah, brilliant idea. So they decided to use it to study radio waves coming from the Milky Way.
So basically trying to listen to the galaxy.
Exactly. Galactic eavesdropping at its finest.
But to do that kind of listening, they needed their measurements to be insanely precise, right?
Oh, absolutely. They had to be super sensitive because they needed to be sure they were picking up real signals from space, not just random interference.
So, like, how did they do that?
Well, Penzias, he was a real meticulous guy, so he built this thing called a cold horn.
Cold horn, okay.
Yeah, it emitted a very, very precisely known signal.
So kind of like a reference point.
Exactly, a reference point.
Right.
So they could compare the antenna's readings to that signal and basically subtract out any unwanted background noise.
So their whole goal was to get rid of noise.
Eliminate it.
Yeah.
But what happened?
Well, they eliminated a lot of noise, but there was this one noise that just wouldn't go away.
That's so interesting.
It was this persistent, low-level hiss.
His slow.
Like, just imagine static on an old radio, but much fainter, and it was there no matter where they pointed the antenna.
So weird.
It was incredibly weird, and they couldn't explain it.
So what did they do?
Well, they were good scientists, so they tried everything they could think of to find the source of this noise.
Like what kind of things?
Well, first they thought maybe it was interference from New York City.
Makes sense.
Yeah, so they pointed the antenna away from the city, but the hiss was still there.
Stubborn hiss.
Then they thought, okay, maybe it's something in the atmosphere.
Yeah.
So they checked different parts of the horizon, different times of day, but nope, the hiss persisted. So it wasn't like the sun or the moon or anything.
No, they even looked at seasonal variations in temperature. They thought maybe that could be affecting something, but nothing seemed to make a difference.
Wow. So at this point, they must have been really stumped.
Oh, they were pulling their hair out. And then there's the story about the pigeons.
The pigeons, I've heard about this. Tell me about the pigeons.
So they had checked every inch of the antenna, right? Every rivet, every wire. And then they found these two pigeons.
Living in the antenna.
Yeah, nesting right inside the feed horn. They made themselves quite comfortable.
Oh, no.
So Penzias and Wilson thought, aha, we found the culprit.
Pigeon interference.
Exactly. They meticulously cleaned out the droppings, captured the pigeons, and even drove them miles away or released them.
Problem solved, right?
You would think. But pigeons are persistent creatures.
Yeah, homing pigeons.
Exactly. They found their way back to the antenna, and guess what? The hiss came back too.
No way.
It was unbelievable. They had tried everything, and this mysterious noise just wouldn't go away.
So they essentially gave up.
Well, not exactly. They had reached the limits of what they could do to eliminate the noise.
So what did they do?
Well, around the same time they were doing all this, there was a group of physicists at Princeton University who were working on a completely different problem.
A different problem. Okay.
Yeah. They were trying to figure out what the universe would look like if the Big Bang theory was correct.
Ah, so like the afterglow of the Big Bang.
Exactly. And their calculations predicted that there should be this faint background radiation filling the entire universe, kind of like a leftover heat signature from the Big Bang.
Wow.
And so Penzias and Wilson heard about this work, and it suddenly dawned on them, could this unexplained hiss they were picking up be that very cosmic background radiation?
Oh, wow. That's a huge leap.
It was. And it turned out they were absolutely right. Their accidental discovery of this annoying hiss ended up being one of the most important confirmations of the Big Bang Theory.
That's incredible.
It's mind-blowing, right?
Mm-hmm.
This seemingly insignificant noise turned out to be a fundamental piece of the cosmic puzzle.
So they basically stumbled upon evidence for the Big Bang.
Stumble is an understatement.
Yeah.
This accidental discovery earned them the Nobel Prize in Physics in 1978.
Well-deserved, I'd say. But it's interesting to think that for a long time, people didn't even have the concept of the Big Bang.
Right, like,
Yeah.
how did people make sense of the universe before we had all this modern knowledge?
Yeah, like let's rewind for a second and think about those ancient views of the cosmos.
So imagine you're looking up at the night sky thousands of years ago. No telescopes, no fancy instruments, just your eyes and your imagination.
Right, just the stars.
And you're trying to make sense of these patterns of light and darkness,
Yeah.
the sun, the moon, the planets, all moving in these seemingly predictable ways.
So what kind of explanations did people come up with?
Well, naturally, they turn to myths and legends.
Like gods and monsters and stuff?
Exactly. Gods and goddesses, celestial beings, all sorts of supernatural forces controlling the heavens.
Okay, but then the ancient Greeks, they started to develop more systematic ideas, right?
Yes, the Greeks, they were really into logic and geometry, and they wanted to find more rational explanations for what they were seeing in the sky.
And they came up with the idea of spheres, right?
Yes, Plato, he imagined the universe as a series of nested spheres with the Earth at the center and everything else revolving around it.
So Earth is still the center of everything at this point.
Exactly, the geocentric model.
Okay.
And then Aristotle came along and he took this idea of spheres even further. He thought these spheres weren't just abstract concepts, but actual physical entities made of this perfect substance called ether.
Ether, okay.
Yeah, and to explain the complex movements of the planets and stars, he added more spheres, counter-rotating spheres, all sorts of intricate mechanisms.
So basically a really complicated clockwork universe.
Exactly, and his model ended up with something like 56 spheres.
56 spheres.
It was a pretty elaborate system.
Yeah, I can imagine. But then Ptolemy came along and tried to simplify things a bit, right?
Yeah, Ptolemy, he lived in Alexandria around the 2nd century AD, and he compiled all the astronomical knowledge of his time.
So he was like the Carl Sagan of his day.
In a way, yeah, he wrote this incredibly influential book called the Almagest, which became like the astronomy Bible for over 1,000 years.
And his model was still geocentric, right?
Yes, Earth was still at the center, but he managed to explain the observed motions of the celestial bodies with a slightly more manageable 40 spheres.
40 spheres, still pretty complex.
It was, but it was remarkably accurate for its time, and it worked well enough to satisfy people for centuries.
So this idea of a universe made of spheres, it really dominated Western thought for a long time.
It did. It was a powerful idea that fit with the prevailing philosophical and religious views of the time.
But then Galileo came along and everything changed, right?
Well, not everything, but he certainly shook things up. Galileo was one of the first people to point a telescope at the sky, and what he saw completely revolutionized our understanding of the universe.
Like, what did he see?
For one thing, he saw that the moon wasn't this perfect smooth sphere that everyone had thought it was. It was actually covered in craters and mountains. He also discovered 4 moons orbiting Jupiter, which provided strong evidence against the geocentric model.
Because it showed that not everything revolved around the Earth.
Exactly. And his observations of the phases of Venus further supported the idea that the planets orbit the sun, not the Earth.
So this was the beginning of the heliocentric model, the sun at the center.
Yes, and it was a radical shift in perspective. But it took time for these ideas to be fully accepted.
Makes sense.
And over the next few centuries, telescopes got better and better, and astronomers started to discover more and more objects in the sky.
More planets, more stars, more everything.
Exactly. They found new moons, new planets, new stars, and they started to realize that the universe was vastly bigger than they had ever imagined.
It's amazing to think how much our view of the universe has expanded just in the last few centuries.
It really is from a cozy little system of spheres to this vast and ever-expanding cosmos.
And speaking of expanding cosmos, that brings us to another really key figure in our story, Edwin Hubble.
Ah, yes. Hubble, the man who showed us that the universe is not static, but is actually expanding.
And that was a huge deal, right?
It was a monumental discovery. It completely changed our understanding of the universe's history and its future.
So how did Hubble figure this out?
Well, he was studying these fuzzy patches of light called nebulae.
Nebulae.
Yeah, and at the time there was a big debate about what these nebulae actually were. Some astronomers thought they were clouds of gas and dust within our own Milky Way galaxy.
Right.
while others thought they might be entire galaxies far beyond our own, these island universes, as they were called.
Island universes. I like that.
It's a great term, right? And Hubble, he had access to this powerful new telescope, the 100-inch Hooker telescope at Mount Wilson Observatory.
Oh, wow. That must have been impressive back then.
It was the most powerful telescope in the world at the time, and he used it to study these nebulae in incredible detail.
And what did he find?
Well, he found that some of these nebulae were definitely not clouds of gas and dust within our galaxy. They were actually incredibly distant collections of stars, entire galaxies, just like our own Milky Way.
So he proved that these island universes were real.
He did, and he even managed to measure the distances to some of these galaxies.
How do you even measure the distance to a galaxy?
It's tricky, but he used a special type of star called a Cepheid variable.
Cepheid variable. Okay.
Yeah, these stars, they pulsate, they brighten and dim in a very predictable way, and the period of their pulsation is directly related to their intrinsic brightness.
So basically, the longer the pulsation period, the brighter the star.
Exactly, and by comparing the apparent brightness of these Cepheid variables in distant galaxies to their known intrinsic brightness, Hubble could calculate how far away they were.
That's so clever.
It's ingenious, right? And what's even more amazing is that while he was measuring these distances, he noticed something really strange.
What was that?
The farther away a galaxy was, the faster it seemed to be moving away from us.
So the universe wasn't just expanding, it was accelerating.
Well, he didn't know about the acceleration part yet, but he did discover that the universe was expanding, and this expansion was happening in all directions.
Like a balloon being inflated.
Exactly. And this discovery was absolutely groundbreaking. It completely changed our understanding of the universe, and it led to the development of the Big Bang Theory.
So Hubble's work was a real turning point in cosmology.
It was a paradigm shift. It ushered in the era of modern cosmology, where astronomers began to think about the universe's history, its evolution, and its large-scale structure.
And this is where Vera Rubin's work comes in, right? She made some really crucial contributions to our understanding of galaxies.
Vera Rubin, she was a remarkable astronomer, and she made some absolutely fundamental discoveries about how galaxies rotate.
So tell me about her. What was she like?
Well, she was very driven and passionate about astronomy from a young age. She was fascinated by the stars and the movements of celestial objects. She even built her own telescope as a teenager.
Wow, that's dedication.
It is, and she faced a lot of challenges along the way.
Like what kind of challenges?
Well, in the 1940s and 50s, astronomy was a very male-dominated field, and women were often discouraged from pursuing careers in science.
Right.
But Rubin, she was determined. She earned a bachelor's degree in astronomy from Vassar College and then a master's degree from Cornell University.
And she was really interested in how galaxies rotate, right?
Yes, that was her main focus. And she made some truly groundbreaking observations in the 1960s and 70s.
So what did she find?
Well, she and her colleague Kent Ford, they were studying the Andromeda Galaxy.
The Andromeda Galaxy, okay.
It's our closest large spiral galaxy, and they were using a new instrument called an image tube spectrograph.
Image tube spectrograph sounds complicated.
It is, but basically it allowed them to measure the velocities of stars in the Andromeda Galaxy with much greater precision than ever before.
Okay, so they were measuring how fast the stars were moving.
Exactly. And what they expected to find was that the stars in the outer regions of the galaxy would be moving much slower than the stars closer to the center.
Kind of like how the planets in our solar system orbit the sun.
Exactly. The planets closer to the sun, they orbit faster. The planets farther away, they orbit slower.
Makes sense.
Right, because most of the mass in our solar system is concentrated in the sun.
Right.
So they thought the same would be true for galaxies. Most of the mass would be concentrated in the center, and the stars would orbit accordingly.
But that's not what they found.
No, they found something completely unexpected. The stars in the outer regions of the Andromeda Galaxy were orbiting just as fast as the stars closer to the center.
What?
Yeah, it was a total surprise. The rotation curve was flat.
Flat rotation curve, okay.
Meaning the orbital velocity of the stars didn't decrease as you moved further away from the center.
So what did that mean?
It meant that there had to be a lot more mass in the Andromeda Galaxy than they could see just based on the stars and gas.
Like there was some invisible mass holding the galaxy together.
Exactly. And this invisible mass became known as dark matter.
Dark matter. Okay, so this is where things start to get really weird.
It does get weird because dark matter doesn't interact with light, so we can't see it directly.
So how do we know it's even there?
Well, because of its gravitational effects, we can see how it affects the rotation of galaxies, the movement of galaxy clusters, and even the bending of light from distant objects.
So it's like this invisible scaffolding holding the universe together.
That's a great analogy. And astronomers estimate that dark matter makes up about 85% of all the matter in the universe.
85%? That's crazy.
It's mind-boggling, right? We're essentially living in a universe dominated by something we can't even see.
So what is dark matter?
That's the million-dollar question we still don't know for sure.
Telling me.
I know it's frustrating, but scientists have some ideas.
Like what kinds of ideas?
Well, some think it could be made up of exotic particles like WIMPs, weakly interacting massive particles.
WIMPs, okay.
Yeah, or axions. These are hypothetical particles that don't interact with light or ordinary matter very much, which would explain why we haven't been able to detect them yet.
Right.
But there are other possibilities too. Some scientists think dark matter might not be particles at all. It could be some kind of modification to our current understanding of gravity.
So we're still very much in the dark about dark matter.
Pun intended?
Yeah, well played. But the search for dark matter is one of the most exciting areas of research in physics today.
Absolutely. It's a true mystery, and solving it could revolutionize our understanding of the universe.
Okay, so we've talked about dark matter, which is this invisible stuff that holds galaxies together, but now we need to talk about dark energy, which is even weirder.
Dark energy, oh yeah, this is where things get really strange.
I'm ready.
All right, so remember how Hubble discovered that the universe is expanding?
Yeah, like a balloon being inflated.
Right. Well, for a long time, astronomers thought that this expansion would be slowing down over time.
Makes sense, right? Everything in the universe is pulling on everything else with gravity.
Exactly. Gravity should be acting like a brake, slowing down the expansion.
But then in the late 1990s, two teams of astronomers made a shocking discovery.
They were studying distant supernovae. These are exploding stars that are incredibly bright.
Supernovae.
And they can be used as standard candles, meaning we know how bright they actually are.
So by measuring how bright they appear to us, we can calculate how far away they are.
Precisely. And what these astronomers found was that the distant supernovae were dimmer than they should be.
Dimmer, that means they were farther away than expected.
Exactly. And this meant that the expansion of the universe wasn't slowing down, it was speeding up.
Speeding up? What?
Yeah, accelerating as if something was pushing the universe apart.
And that something is dark energy.
You got it. Dark energy is this mysterious force that seems to be counteracting gravity, causing the expansion of the universe to accelerate.
So it's like anti-gravity.
In a way, yeah, it's a repulsive force that's pushing everything apart.
And we have no idea what it is?
Not really. We know it's there because we can see its effects, but we don't know what it's made of or how it works.
So dark energy is like the ultimate cosmic mystery.
It is. And it's even more mysterious than dark matter because it makes up an even larger portion of the universe.
How much larger?
Astronomers estimate that dark energy accounts for about 70% of the total energy density of the universe.
70%. So dark matter and dark energy together, they make up like 95% of the universe.
Yeah, pretty much everything we can see, all the stars and galaxies and planets and us, it's all just a tiny fraction of what's really out there.
That's mind-blowing.
It really is. It shows us how much we still don't know about the universe.
So where do we go from here?
Well, scientists are working hard to try to understand dark matter and dark energy better.
Like how?
They're building new telescopes and detectors, trying to observe these phenomena more directly. They're running computer simulations to model how dark matter and dark energy behave, and they're developing new theories to explain what they might be.
So it's a really active area of research.
Absolutely. It's one of the most exciting and challenging frontiers in modern physics.
So to recap our journey through the universe's ingredients, we started with the surprising discovery of the cosmic microwave background radiation, that faint hiss that confirmed the Big Bang.
Yes, and then we explored the evidence for dark matter, from the unexpected rotation of galaxies to the large-scale structure of the universe.
And finally, we delved into the mystery of dark energy, this enigmatic force that's accelerating the expansion of the universe.
And the big takeaway from all this is that our understanding of the universe is constantly evolving.
It's a story that's still being written.
Exactly, and there's still so many questions to be answered.
So what's the next chapter in this cosmic story?
Well, only time will tell, but I have a feeling it's going to be even more mind-blowing than what we've discovered so far.
So what do you think, what new noises might we discover that could lead to even bigger breakthroughs in our understanding of the universe?
That's a great question. Maybe we'll find some unexpected signal in the gravitational waves from merging black holes. Or maybe we'll detect particles that interact even more weakly than WIMPs.
Or maybe it'll be something completely different, something we haven't even imagined yet.
Exactly. The universe is full of surprises, and that's what makes it so fascinating to study.
Well, on that note, thanks for joining us on this deep dive into the mysteries of the universe. It's been a truly mind-expanding journey.
It has. And hopefully it sparks some curiosity and a desire to learn even more.
So keep looking up, keep exploring, and who knows, maybe you'll be the one to make the next big discovery.
Absolutely, the universe is waiting to be explored.
And until next time, happy deep diving.
Happy diving.
Guys, see you in another podcast. Don't forget to subscribe to our channel.